A helicopter skims Japan's coastline. Below, a wall taller than a four-story building runs to the horizon, 400 kilometers of concrete between the Pacific and the people who refuse to leave. $12 billion, every meter paid for in grief. Sensors buried inside track each millimeter of movement, because the ocean never stops testing the stone. The engineers who built it issued one warning. If this wall fails, it makes the next tsunami deadlier than the one that demanded it. Before the new wall existed, Japan already had seawalls. Thousands of kilometers of them, guarding nearly every populated stretch of coast. On March 11, 2011, the ocean floor lurched 50 meters in 3 minutes. Not a tremor. A geological rupture tearing across 500 kilometers of seafloor. The Pacific didn't ripple. It mobilized. What crossed Japan's coast 30 minutes later wasn't a wave. It was a moving wall of black water, 40 meters tall at its peak, and it treated everything in its path as debris. 90% of Japan's seawalls failed in a single hour. The ocean didn't overpower them from the front. It climbed over them. Water cleared the top, found the unprotected back face, and clawed the foundations out from underneath. The walls didn't shatter. They were swallowed from behind. The kill mechanism was overtopping, and almost nothing in Japan's entire coastal defense had been designed to survive it. The world's largest breakwater stood at Kamaishi. $1.6 billion of engineered concrete, a structure that took decades to design and build, positioned to be unbreakable. The tsunami erased it in seconds. Water poured over the crest, attacked the landward side, and the foundation soil liquefied under the assault. A generation of engineering vanished in less time than it takes to boil water. 18,000 people died that day. Entire towns ceased to exist between breakfast and lunch. But one village survived, not because its wall was smarter, not because the ocean showed mercy. One mayor had spent years fighting his own residents over a wall they thought was too tall, too expensive, too ugly. He won the argument. 3,000 people lived because of it. That single political fight, waged in meeting rooms years before the wave arrived, gave Japan its blueprint for what came next. The blueprint was simple: build taller. But the engineering underneath that sentence would consume a decade, $12 billion, and 440 separate construction teams racing to build simultaneously along 400 kilometers of active coastline, the same coastline the ocean had already proven it could swallow whole. Most of the wall is underground. Only 14 meters show above the surface. Everything holding it upright hides beneath the seabed, and the seabed is actively trying to destroy it. Before a single stone touches the coast, survey ships drill the ocean floor to map what waits below. Every kilometer reveals something different. Soft clay that swallows anything heavy. Dense sand that shifts under pressure. Hard rock that shatters drill bits. Each demands completely different engineering underneath, and getting it wrong means the wall above slowly tilts, cracks, and feeds itself to the tide. Engineers modeled each section 200 times in a computer before committing a single boulder to the water. 440 separate teams worked simultaneously, and if even one contractor went bankrupt mid-build, a gap would open in the wall. The ocean doesn't negotiate with gaps. The tide dictated everything. 4 hours of exposed seabed per day. Every minute accounted for. Every task sequenced against the water's return. In clay zones, the ground was so dangerously soft it couldn't support a bulldozer. Steel road plates spread the machine's weight so it floated above mud that would have devoured it. Simple, effective, and repeated for kilometers of coastline where the earth refused to cooperate. Then the work moved underwater. Divers guided 5-ton boulders into position in the same ocean that had just destroyed the coast, while engineers tracked their progress by sonar alone. Nobody could see the foundation taking shape. They trusted the data, or they trusted nothing. Between the boulders and the fill material sat a filter layer, a membrane so critical that missing it in a single section would let the wall slowly bleed its foundation into the sea, grain by grain, until the structure above had nothing left to stand on. After weeks of blind underwater construction, the rubble mound finally broke the surface. The foundation existed, but now the wall had to rise into open air, and every layer it gained made it heavier, less forgiving, and more vulnerable to the thing that had killed every wall before it: rain. The first steel goes into the ocean floor, not upward. Sheet piles driven 10 meters deep protect the wall's toe, but not from the arriving wave, from the retreating one. Backwash, the vacuum of water pulling back toward the sea, is what murders foundations. It sucks the sand out from under the structure and leaves the wall standing on nothing. The arriving tsunami gets the attention. The departing water does the killing. One buried boulder deflects a 12-meter pile sideways, and the entire alignment is destroyed. The fix is brutal. Pre-drill the boulder, crush it in place, then drive the pile straight through the cleared hole. Clean. But every obstruction costs hours the schedule doesn't have. Above the piles, fill arrives in 300-millimeter lifts, no thicker. A compactor can't reach the bottom of anything deeper, and uncompacted fill settles unevenly, and a settling foundation tilts the wall. Geotextile reinforcement layers run through the body like tendons, holding compacted earth together the way rebar holds concrete. Every single layer is tested. 98%. Proctor density, or the inspector, shuts the job down. Press your foot on fill compacted to 98%, and nothing moves. At 85%, it sinks beneath you. 30 dump trucks running 16-hour shifts fed the wall non-stop. One breakdown stalled the entire compaction cycle. 300 millimeters per day, 18 months until the first tsunami season with the wall standing. The math left no margin. Then a single night of heavy rain erased weeks of progress. 600 millimeters of completed slope slumped away in the dark. The entire section was rebuilt from scratch. After that, every slope was covered with geotextile before every rainfall, no exceptions. The rain had taught the crews what the ocean already knew. Water doesn't need to arrive as a tsunami to destroy a wall. At 10 meters, the earthwork stopped, and the first 7-ton concrete panels arrived, slabs that would take a tsunami at 30 kilometers per hour and hold their ground for 100 years, provided every millimeter of their casting was perfect. A technician taps a freshly cast panel with a hammer. A solid ring means good concrete. A hollow sound means the panel gets crushed. 7 tons, $800, destroyed on the spot. Zero tolerance on tsunami walls. The wall demands perfection, and it enforces that demand by consuming its own components. Wrong concrete slump, and the panel face honeycombs, tiny air pockets that become entry points for salt water, then corrosion, then failure under wave pressure. One bad batch condemns the entire production run. Self-compacting concrete flows around every hairpin bar connecting panel to crown wall, filling every void, leaving a surface smooth enough to deflect a tsunami without giving it anywhere to grip. One missing bar breaks the connection. One void compromises the face. 7-ton panels travel narrow Japanese coastal roads, flagmen stationed at every junction, across 400 kilometers of delivery routes. The transport bed is leveled to 5 millimeters. A single hump cracks a corner, and the panel joins the crusher pile. The tolerances don't loosen because the logistics are difficult. They tighten. Straight panels meeting a curved coastline open 20-millimeter gaps, and water finds everyone. It forces through, attacks the fill behind, undermines everything below. 37 unique panel shapes, each cast in CNC machined molds, close every gap to zero. Rubber water stops line each joint. material engineered to swell on contact with moisture. The bigger the wave, the tighter every joint seals itself. The tsunami activates its own containment. Behind the panels, 32-ton tetrapods armor the landward face. They are not placed precisely. They are dropped. Each one finds its own stable position, one leg always pointing upward to catch the next tetrapod above. Chaos creating order. The gaps between them are the mechanism, not a flaw. Water flows through, energy dissipates across thousands of interlocking surfaces, a single leader absorbed completely. Now multiply that by 50 million tons of tsunami, pushing against the coast. 400 kilometers of wall, armored and sealed, but 443 holes punched straight through it. Every river mouth, every harbor entrance, every road crossing the coastline is a gap, and each gap is a death trap if the single gate covering it fails to close in time. A seismic sensor fires. Somewhere along 400 kilometers of coastline, a floodgate begins closing. 70 seconds. That is the entire window between the earthquake and the wave reaching the coast. The gate does not ask permission. It does not wait for confirmation. It moves. Floodgate concrete runs twice the thickness of the wall itself, because this is exactly where tsunami forces concentrate hardest. The wave doesn't spread evenly across the barrier. It hunts for openings and throws its full weight into them. 50 tons of steel swing on 15 millimeters of clearance during installation in 40 km/h coastal winds. The margin between a gate that seals and a gate that jams is thinner than a human finger. 14 seals line each gate. If one leaks, the gate fails completely. 40 liters per minute pour through a 2-millimeter gap under normal water pressure. Under real tsunami loading, that gap stretches to 20 millimeters, and 40 liters becomes a flood. Engineers grind 2 millimeters off a seal face, retest, confirm zero leakage. 3 hours of machining saves an entire town. The seal doesn't care about the cost, it cares about contact. River mouths demand something larger. A 22-meter steel curtain hangs stored open above the channel, waiting. Gravity closes it. Power failure doesn't stop it. Human absence doesn't stop it. The earthquake begins, and the curtain drops, sealing the river mouth before the wave turns the channel into a funnel, aimed directly at the town behind it. 443 gates. 1 command room. 4 minutes and 20 seconds to confirm every single one has sealed. Japan rehearses this every March 11th, the anniversary serving as both memorial and operational drill. A driver caught in the gap when the alarm triggers faces the same 70-second window the gate does. The system does not distinguish between obstacles. The gates sealed during drills hundreds of times. But on the day a real 7.4 earthquake struck, every sensor in the wall fired simultaneously. All 443 gates closed at once, and the engineers who built them watched their screens and waited for damage reports from a system that had never been tested by the thing it was designed to survive. 0 cracks. 0 shifted tetrapods. The damage reports came back from every section of the wall, and the numbers were almost unreasonable. 14 millimeters of differential settlement across 400 kilometers in 2 years on coastal sandy ground. Engineers expected worse. The ground had every reason to move, and it barely whispered. The wall didn't survive because it was rigid. It survived because it was designed to breathe. Sensors embedded inside the concrete track every millimeter of movement, every shift in pressure, every slow exhale of settling fill. Engineers watch the data every single day. The monitoring never stops because the wall is not a finished object. It is a living system under permanent observation, and the ocean is permanently probing it for weakness. At Kamaishi, where the tsunami had erased the world's largest breakwater in seconds, a new structure now stands. 60,000-ton caissons, sunk to 63 meters. The rebuilt breakwater is stronger than the world record it replaced. 2 millimeters of carbonation seal the concrete surface. The reinforcement inside will not taste sea air for at least 100 years. The ocean took Kamaishi's wall once. The replacement was built to make sure the ocean remembers. A helicopter flies the full 400 kilometers. What it photographs looks like a gray line drawn between the land and the sea. From above, the wall reveals nothing of what lives inside it. The sensors, the tendons, the drains, the hairpin bars, the filter layers silently holding everything in place. But at ground level, people cycle along the top. They walk dogs. They run every morning. Staircases built into the face are not scenic overlooks. They are evacuation routes designed from crowdflow science. The wall was built from grief. It became part of daily life. And every morning it stands, it is negotiating with an ocean that has not agreed to stop. Somewhere in the North Atlantic, engineers are solving the opposite problem, forcing an entire ocean current through a 2-kilometer gap to power a nation. 4 million cubic meters per second, funneled through concrete that doesn't exist yet. The first pour happens this decade. Subscribe to see what they're building.